All right, good morning, everyone. Let's do it. So, any questions before I begin? Y'all feeling pretty excited today? Oh, wow, that's some energy. All right, what are we doing today? We're going to start, we were doing antiderivatives last time, right? So going backwards, trying to figure out if we can figure out the function that gives us a derivative of something. So this is not your stuff, no. This is different notes. So what I wanted to do was start with, I guess, where we're headed with the next day, 3 days of class, right? What the goal is going to be, and then it's going to take me a little bit of time to develop the idea. But I want to give you kind of the general overview of it. So we have something in calculus called the fundamental theorem of calculus, all right, which sounds pretty important, right? And the basic idea is this. If you were to take a function, right, Cal1 is about finding the slope of the tangent line on that, for that curve, right? Go to a point, using differentiation, we should be able to find the slope of the tangent line. And then we can use that to do all sorts of things, figure out where it's going up and down and maxes and mins and all that stuff. In Cal2, the question we're going to ask is this. If I were to start the function at a point, draw it, stop at another point, let's say this point is A, and let's say this point is B, the question is, can we figure out what that area is for any function? Pretty simple geometric idea, right? But not easy to actually execute in terms of, well, it's going to require some work, right, to do that. But imagine, if you will, historically, we could find the area of lots of objects, right? Think about the things that we could find the area of right now, right? Like a rectangle. We all know the area of a rectangle is whatever the length is times the width, right? Area is length times width. If we have a triangle, then we can say, okay, this is the height, and then this is the base, and then the area is 1/2 base times height, right? Lots of objects we can find the area of already. And historically, humans had no problem finding the areas of these things. But in the real world, things are not always rectangles and they're not always triangles. So as humans started to fight over land, right, at some point we started to say, hey, this is mine, stay away, right? We started to create borders and things like that. We needed to find the areas of, maybe you had a river and maybe you owned this property here, right? You want to know, what's the area of that property? Well, these aren't straight lines, right? So how do you find the area of that? Well, this is kind of that idea, right? We want to be able to find the area underneath some arbitrary function. And so do we have a method for that? Understand? And so the first people to actually, as far as we can tell historically, the first people to actually tackle this problem in a systematic approach were the Chinese, and they did it thousands of years ago. And the idea is they went after trying to find the area of a circle first, right? So this is before pi r squared was known, right? Like we all know the area of a circle is pi r squared, but before that formula was known, how did humans do it? So let's say we have a circle. What the Chinese did was they said, all right, let's approximate the area. Okay, so let me approximate this area. I'm going to draw a square or a rectangle, whatever you want to draw. Do you all agree that the area of that square is less than the area of the true circle? Yes? So we've got all these little regions here that we did not account for, right? Those regions would be considered the error, right? That would be the error that we would get if we said, oh, the area of that circle is really like that square. So then the Chinese said, okay, let us do better, and let's start filling in those gaps with rectangles. That's better, right? If I take the square and then I add up these rectangle areas, that should give me a better approximation. Would you agree? Okay, and then they say, all right, well, we still have some error, don't we? These little gaps here. So let's fill those in with little squares and rectangles and just kind of see what we can get in here, right? That's better, isn't it? I'm getting closer and closer to the true area, aren't I? But I'm never actually going to get there because there's no way that I can fill in all the little gaps, right? But that's what the Chinese did. They tried to. They drew very precise circles, and they drew very precise rectangles and squares, and they measured the lengths, and they tried to find some relationship that would give them the area of a circle, all right? And they did it pretty damn good. They got a pretty good approximation. So let's say we're doing this, right? The Chinese did this, and they said, okay, let's add up all these rectangles, and that's going to be, let's call that A small. I'm going to call it A small. They probably didn't call it A small, but this right here is the area, but it's too small, right? It's not enough because of all the little gaps I missed, right? So then when they would come through and they would say, okay, well, how about this square? What's the area of that square? Well, that's too much, right? But they could measure the area of that square. And then they would come in and they would subtract all these little rectangles. And do you all see that when you do it that way, if you take the area of the big blue square and you start subtracting all those little blue squares, right? That area is going to be too what? Compared to the original. Too big, right? That's too big. But you could get pretty close, the more precise and more rectangles you did. Right? So they would come up with an area that would be too big, right? And what they knew is that the true area, right? The true area was between these two numbers. Right? It's got to be. That one was too small, that one's too big. So the true area, which I'll just call area, I'll put true, is somewhere between those two. And man, they spent, hundreds of years trying to get this better and better and better and better and better, right? People would spend their lifetime drawing rectangles, and I'm exaggerating probably, but you get the idea, right? And this method for doing this is called the method of exhaustion. Believe it, that makes sense? This would be kind of exhausting to do this. But they were able to determine that the area of a circle is approximately 22 over 7 times the radius squared. They were able to deduce that. Now, if you do 22 divided by 7 on your calculator, anybody have their calculator out? Do 22 divided by 7, tell me what you get. Okay, so 3 point what? 1,4, what else? 2,857. Okay, let's stop there. Okay, now, what's pi? We know the real answer is pi, right? So pi is 3.1415 something else. You can see that, they were off. The first number was right, this was right, that was right. This is where things kind of fell apart for them. But for most practical purposes, 22 over 7 back in the ancient days was good enough because they couldn't manufacture things like steel ball bearings where you had to be real precise anyway, right? They're building stuff, very rudimentary things, right? So it was good enough. That was good enough for a long time. But eventually, we needed the exact actual area. So this idea, okay, was with us for a long time until calculus came around. And then what we did in calculus is we said, you know what? Let's approach this from a different perspective. We're still going to kind of use a method of exhaustion, but instead of looking at a circle, let's just look at an arbitrary function. Let's try and find something generally. And if we can find a general formula for finding areas, then the circle should be pretty easy because a circle, think about if you were to graph it, right? If you graph just a quarter of a circle, do you all agree that that's a function? Like it passes the vertical line test? So if I look at this as some function f, if it starts here and stops here, then I can try and find the area underneath this, and that would be 1/4 of the whole circle, right? So whatever this area was, I just multiply that times 4, that would give me the area of the circle. So we tried to look at more generally first. Well, first it was this, but then with the calculus we said, can we do it more generally, all right? So that's what we're going to do right now. is I'm going to show you how we developed a formula for doing this. All right? You ready? You get the idea? Okay. Before I actually do the formula, I have to establish a few things with you. So if I ask you right now, so this is like some preliminary things. All right, if I ask you to take 1 plus 2 plus 3 plus 4, and let's say I ask you to stop at 100. Nobody in here is going to be able to tell me what that is, I don't think, unless they get their calculator out and do that, right? That'd be a pain in the ass to do that. So this is called a finite sum. Okay, it's a sum, right? We're adding things up, and it's finite, meaning that there's a finite number of terms. There's a special notation that we use whenever we have finite sums or even infinite sums. We use this thing called sigma notation. So this is what this little note's about. You all seen that symbol before? That's the capital Greek letter S. S stands for sum. So this is a notation that we use to be able to write this in a more condensed manner. So what we do is on this capital sigma, below it we have what we call our index. And then the index can be any letter you want, but the common letters are I, J, K, and N. I'm going to use N. Let me use K. I put K equals 1. All right, that's basically, I'm telling you that I'm going to start with K being 1. And then what I'm going to do is I'm going to put right here a formula that's going to give you instructions on what to do. Let me just write it first. I'm going to say, just give me K, and then I want you to stop at 100. All right, just look at that for a second, and let me kind of explain what's going on here. So what this is equal to is I'm going to start with K being 1. All right, so K is 1. And what I want to do is spit out K. So what's K? 1? 1. Then, because it's a sigma, I put plus. And now I increase K up to 2. And what do I spit out? Spit out that K again. So now I'm going to spit the 2 out. Plus, now I let K go up again. Now K is 3. Spit out K, it's going to spit out 3. And I keep doing this, and this is where I stop the K at. So I go, start at 1, then go to 2, then 3, then 4, then 5, then 6. Make sense? So this would be this all the way to, all the way to 100, right? This right here, right, is called sigma notation. It's just an easier way to write a sum. All right, how about this? Let me give you a separate example. Let me give you this sigma notation, and y'all tell me what this spits out. Sum K equals 1 to, let's go to 100 again. And this time I want you to spit out K squared. So what's the first number I'm going to get out there? 1. Right, 1 squared is 1. I'll just put 1 squared. Plus, next one is 2, right, but 2 squared. And then 3 squared, and then 4 squared. And I keep doing that until I get to 100 squared, right? Which of course would be 1 plus 4 plus 9 plus 16 plus all the way ... until you get out to 10,000. Understand? All right, let's do one more. Sum K equal, K, I put N. K equals 1 to 100 of, how about K cubed? This time I'm not going to write them out like this. We're just going to do them in our head. 1 cubed is 1. 2 cubed? 8. 3 cubed? 3 times 3 times 3? 27. 4 cubed? 4 times 4 times 4 times 4? What is it? Is it? 4 times 4, 16 times 4, 64. Plus ... What's the very last one? 100 cubed. Yeah. Is it a million, right? It's a million. The more important piece of this is that you have the idea of what the sigma notation means. How many of you had seen sigma notation? A few of you? Okay, yeah. Usually in 1414 we do it. So, all right. Now, I don't want you to be misled here. This formula does not have to be just K's, all right? It can be anything. In fact, Cal 2, I'll show you. I have the notes right here. I'll show you what I'm doing today in my class. Not that one. Just to show you that there's different formulas. There we go. There's sigma notation. I'm using n instead of k. Starting at 0, where does it stop? Never. Okay? And that's the formula. See, the formula here is just k, right? This one is k squared, this one's k cubed. That's the formula. That's the formula for that sigma notation. So it doesn't have to be pretty. It can be pretty ugly. All right. You all good? Sigma notation, basic idea? All right, so what I need to do to develop this idea of the area under the curve is I'm going to look at these three sums in particular. These are very special sums because we actually have a formula that will give you this answer without you having to do much work. All right? So I'm about to give you those formulas. That was just to get you to see what that all means. Some special sums. Let's say I ask you to do this. Sum k equals 1. I want you to stop when you get to n. So this time I'm not telling you what the number is up there to stop at. I'm not putting 100. I'm just saying stop at n. And I want you to do the formula is k. So tell me what this is. Plug in 1, what do you get? 1, right? Plus, now plug in 2, then 3, then 4, right? So this is going to be 1 plus 2 plus 3 plus, I keep going, where do I stop? At n, right? This adds up to be n times n plus 1 divided by 2. Now, I'm not going to prove that to you because we just don't have time to prove that. You're going to have to take that on faith. So let me see if I can show you a specific example of this. Let's say that I wanted you to add 1 plus 2 plus 3 plus 4 plus 5. Let's go one more. If I ask you to add those up, of course you could do that on your calculator, right? We could probably do it in our head, yes? Let's see what this adds up to be. 1 plus 2, 3, 3 plus 3, 6. 6 plus 4 is 10, 15, right? This adds up to be 15. We don't need a calculator for that. However, let's try and use this formula for it. So where did I stop that sum? What was the last number I stopped at? 5, right? That was the n, right? So I'd like you to plug 5 into this formula and tell me what you get. So what's 5 times 5 plus 1? Divided by 2, this is 5 times 6 over 2, which is 30 over 2, which is also 15, isn't it? Coincidence? No, that's always going to work, all right? Always. Another example of this, if I asked you to add 1 plus 2 plus 3 and stop when you get to 100, right? We would not want to do that in our heads. We probably couldn't do that easily in our heads. We could probably get a calculator out and start pounding out that answer, right? But according to the formula, this should be equal to what? 100 times 100 plus 1, 101, all divided by 2. And that you could do on your calculator, right? What does it come out to be? 50-50? right? 50-50? Okay? Nice little convenient formula, huh? Again, I'm not proving this. You just have to know, like, this formula exists. All right, I'm going to give you another formula now. I'm going to give you a total of 3, and then we need those to do what we're going to do. All right? So the next formula is the formula for sum n equals 1 to n of k squared. So this is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. So 1 squared plus 2 squared plus 3 squared plus 4 squared. You get the idea? Stopping at what? N squared. All right, this formula is a weird one. Good news, I have these in your notes. You know what? Hold on. Now I'm thinking about it. Do I have these in your notes? I'll make sure they're there. Okay, here we go. I'll make sure that I put these out. I have the formula we just did is up here. Sum k equals 1 to n of k, which is 1 plus 2 all the way to n. That's n times n plus 1 over 2. Look at the formula for this one, for k squared. It's this right here. I'm going to put these on the side off camera, all right, so I can use them in a minute. So when I do the sum k equals 1 to n of k, right, which is 1 plus 2 plus 3 plus all the way out to n, that's n times n plus 1 all over 2. If I do the sum k equals 1 to n of k squared, that's 1 plus 4 plus 9 plus dot, dot, dot till I get to n squared. That's that formula right there. It's strange. N times n plus 1 times 2n plus 1 all over 6. That's strange, but that's the formula for it. And then the last one that we're going to do in here is the sum of the cubes. 1 plus 8 plus 27 plus all the way till you get to n cubed. And that's the formula for it right here, which is really kind of interesting when students see this. Sometimes they're like, what? That's weird, because isn't it the formula for that one up there, but squared, right? It's that formula, but squared. That seems really weird that it would be that, but that's what it is. All right, I have a lot of stuff on the board here. Let me get this out of here. Does anyone have a question? You all right? Yes?
Sorry.
Yeah.
Notation-wise?
Yes.
The n on top of
The sigma notation, yeah. The n on top.
Does it always be a capital, or does it not matter?
It does not matter. I never write in lowercase, so my n's always look like that. You can do an n like that if you want. I stopped doing n's like that because they look too much like my r's, like I wouldn't curl my r enough or something, so I just started doing that. But yeah. It can be anything you want. All right. Good, good. Yes?
I just want to confirm, so, like, you know how you're showing like 1 and then we go to plus 4 plus 9 plus 16?
Uh-huh.
Is it that we're adding the 1 plus 1 to 2 and then squaring it like k? Like, is that
Wait,
how
are you
it
talking
goes?
on the second one with k squared?
Yeah.
Are you asking?
Like, well, I mean with all of them, like, when we're getting to these second, third, fourth values, is it that we're adding the value
Previous?
before
No.
and the k
Well-
plus 1 together and then squaring that? You know what I mean?
No, yeah, no. Okay, no. You're just, the k is going to start at 1. Let's do this. Okay, so I say, okay, first let k be 1, all right? What is 1 squared? 1, okay? You're done with 1. Now I want you to let k be 2. What's 2 squared? 4, right?
One of the number line,
Plus-
we're adding the last
We're,
one.
we're not, yeah, once we finish with the first k, we go on to the next one. So now I'd say k is what? 3, and now what's 3 squared? 9. Okay, and now I'm done with 3, now I move to 4. Yes? Okay. All right, I said I wasn't going to prove these, right? I want to try and prove the first one just visually. I think I can prove it visually for you, all right? So look at that first formula. I'm going to draw a picture. Let's say that that's a square, and each side is 1 by 1 by 1, okay? 1 by 1 by 1. All right. 2 squares. 3 squares. 4 squares. 5 squares, right? I could keep going, but let's stop there. How many squares are there total? Well, there's 1 plus 2 plus 3 plus 4 plus 5, right? That's how many squares there are total? The way I'm going to try and come up with a formula is I'm going to copy that, right? Computer, I'm going to copy it, paste it. So I'm going to make a copy of this, all right? And I'm going to flip it over. So imagine I take a copy of that and I flip it over and I put it like this. I put the 1 here, the 2 there, the 3 there, the 4 there, and the 5 there. How wide is this? 5, right? How tall is this? 6, right? 1 more than what I started with, right? This was 5, but I turned it over and pasted, so that's 6. So how many squares are there total? Total squares? 30, right? 6 times 5 is 30. But remember, I made a copy, didn't I? So that's twice as much as what I wanted. So if I take this 5 times that 6 and divide it by 2, that's how many squares should be there, right? That's how many black squares there should be, right? Take the total number of squares, divide by 2. That make sense to you? So imagine doing that for n squared, like n. You start with 1, then you go 2, then you go 3, then you go 4, right? And I keep doing this. In my very last column, what if I tell you that there are n squares in that, right? Then I can make a copy of that and flip it over, right? And paste it on there. And I put that first one there. The next 2 would be there. Next 3 would be there. I think you. And then I get back to the very end like this, right? And this is all filled in, isn't it? How many squares do I have this way? Or sorry, how many across the bottom? N. How many tall? N plus 1. So if I multiply the n times n plus 1, that's twice as much, right? So I divide that by 2, and that's your formula. Hope that makes sense. If it doesn't, don't worry, because you just need to know the formula, all right? That's in no way a proof. That's more of a sketch of a proof, a visual proof. All right, I think we're ready. Y'all ready? About to get into it now. So we are now going to discuss, we're getting to the area thing, right? We're going to discuss something called Riemann sums. Riemann was a mathematician, right? Famous mathematician. His last name is Riemann. I don't know his first name. But this concept came from Riemann, or he perfected it, I guess you could say. All right, look, let me just put a little disclaimer here. Not a disclaimer, but just what I want you to do right now is see if you can understand what I'm doing. At the end of the day, I'm not going to ask you to do any of this on a test, all right? Because this is going to be really tedious and ugly, and it's going to be a mess. And then the fundamental theorem of calculus comes and saves us and actually makes the problem simple, right? But you have to see the development of it, because it's critical in Cal 2 that you understand the geometry of what's going on right here. All right, y'all hear me? So I don't want you to tune me out, but I want you to pay attention, and don't ask questions, all right, if you have a question. All right, so here's what I'm doing. We're going to try and do this Do I want to do a specific, let's do a specific example. Let's say I take the function f of x equals x squared, and let's look at it between 0 and 2. So what's that value up here? How high is this point? 4, right? That's 4. 2 squared is 4. I'm looking at that parabola. I'm only looking at it between 0 and 2. And what I'm interested in here is if we can find the exact area below this graph and above the x-axis. That's what I want us to be able to find, all right? Well, it's definitely not a rectangle, right? So we're not going to be able to just use a rectangle. But what I could do, right, what I could do is I could approximate this like the Chinese did with the circle. I could approximate this with a rectangle, couldn't I? So I could do something like this. Now, this graph is a little bit off from this one. Please ignore it. This one I'm only going from 0 to 2. Over here, I'm going from 1 to 5. Don't worry so much about that right now, all right? This is a parabola, right? I'm trying to find the area underneath it. Do you all agree that the gray rectangle is an approximation? And it sucks, right? It's a really, really crappy approximation. How did I get that gray rectangle? I went all the way across the interval, right? I said 5 this way. I mean, from 1 to 5 this way. And then to get the height of this rectangle, what I did is I took the number 5, I plugged it into the function. What's 5 squared? 25, right? And it got that point, and that gave me this side was 25. And this length from here to here, from 1 to 5 would be 4. So the area of that rectangle is 100, isn't it? 4 times 25, that's 100. So you can see the estimated area I have right now is 100. The true area, which you're just going to have to believe me right now, that's the true area of this. We're off by a lot, aren't we? But I only use one rectangle. That would be like when the Chinese only used one square. I get a better approximation if I use more rectangles. So let me start the whole thing over, and let me do 2 rectangles. So if I do 2 rectangles, what I would have to do is first find the area of this first rectangle, and then this area of the second one. How wide is this rectangle? 2, right? How tall is it? How are you going to get that? It's right here, right? That's this point. 3 goes into the function and becomes 3 squared is 9, right? So isn't that 9? See, I'm plugging that right endpoint into the function to get how tall it is. Yes?
What would be 2 and a 3 for the x-axis?
I'm going from 1 to 3.